rectangular plane strings by matrix stiffness method. So straight away we will take a problem and explain the procedure for that. So as we hear, let us consider a rigid rectangular plane frame. It's a rectangular rigid plane frame because all members lie in one plane and all members are perfectly orthogonal to each other, not inclined like members. They are all orthogonally inclined members. It is called rectangular frames. And we will consider a rigid rectangular frame subjected to these loadings. So let us analyze this rigid rectangular plane frame ABCD subjected to a joint load of 20 kilonewtons acting at the joint B and a member load of 90 kilonewtons acting on member BC as in the figure. So as usual, the first step, we have to find the kinematic indeterminacy. The kinematic indeterminacy of this particular frame is 3. The maximum kinematic indeterminacy as per syllabus. So they are, you can just mark all the unknown displacements kinematic indeterminacy. That is coordinates of unknown joint displacement. The unknown joint displacements are, one is this here, so this is 1, 1. The coordinate is, it indicates positive direction of the unknown displacement, horizontal displacement. Vertical displacement at these two joints are not there because we assume all members to be axially rigid. So vertical displacements are 0 and only the rotations. Rotation here 2, rotation here 3. And here no displacement because they are fixed ends. So only the unknown displacements are 3. One horizontal displacement, that is sway, and another 2 rotations like that. So these are the coordinate directions of the unknown displacements. And unknown member forces which we have to determine during analysis are, we choose the end moments at the ends of member as the unknown to be determined during analysis. Like this, we have to determine the moments at the ends of all members. Member AB, we have to determine the end moments. This is 1, 2, that is MAB, MBA we have to determine, then MBC, MCD, then MCD, MBC. These are the coordinate directions of the moments which we have to determine during analysis. These coordinates are indicated as 1, 2, 3, 4, 5, 6. That is, 1 indicates represent MAB, 2 indicates MBA, 3 MBC, 4 MCD, MCD is 5, MBC is 6. These are the coordinates of unknown member end moments. Member end moments to be determined during analysis. During analysis. So this is nothing but our TM matrix. This is nothing but our T matrix as per our notations. Therefore, D to be determined are D1 and D2. That's the displacement along the coordinate 1, 2 and 3. 3 displacements we have to determine. So this is a 3 by 1 matrix, and unknown member in sources to be determined are this PM1, PM2, PM3, PM4, 5 and 6. PM6. So this is the 6 by 1 matrix. So these are the two matrices which we have to determine during our analysis. That's the first step. Then the second step, or here itself in the first step, you can find out EMF, that is unknown member and actions. So that is PMF is equal to, that is the member and forces corresponding to these PM matrices due to the member loading. So here on AB there is no member loading, so moments corresponding to coordinates 1 and 2, that's MAB, MBA, it is 0, 0, right? Then on BC, on MBC, that is corresponding to 3, it is WAB squared by L squared, that is 90 into 4 into 2 square divided by L square, that is 36. So this will become 40. This is minus, because here moment, fixed and moment is anti-clockwise, we have taken this clockwise as positive, so that's minus 40. And this corresponding to 4, it is 90 into 4 square divided into 2 divided by 36. This is 80. We are getting that as 80. Then corresponding to 5 and 6, there is no member loading, so it is 0, 0. This is again a 6 by 1 matrix, that is PMF corresponding to fixed and moments. Then PD, that is the load, equivalent joint load corresponding to this kinematic indeterminacy, that corresponds to 1, 2 and 3 coordinates, which is nothing but Pj minus PMF. So this is nothing but corresponding to 1, you have a load here, joint load, that is 20. Corresponding to this, here in the horizontal direction there is no other load, MF, so it is just 20 itself. Then corresponding to 2, it is moment here corresponding to 2 and 3. So that is corresponding to 2, it is 0, corresponds to 3, it is minus 40. So it is minus of minus, so it is plus 40. Then corresponds to 3, it is 4 and 5. So this is 0, this is 80, so this is minus 80. This is 3 by 1 matrix, same as D. This PD and D, they are of same order, and PMF and PM, they are of same order. That is due to the given loading, whatever fixed and moments you are, that you are calculating corresponding to PM, and equivalent joint load corresponding to D, you are calculating from here. This is your first step. Then second step, to find stiffness matrix. Stiffness matrix K. This is an important step which actually involves our calculation. This is of course self-explanatory, easily you can do it, but only K computation is the main exercise. Here first of all, the size of stiffness matrix you have to determine. That I told you, since kinematic indeterminacy is 3, stiffness of order of stiffness matrix is 3 by 3. So that is first step you have to do. Since the kinematic indeterminacy is 3, size of stiffness matrix, size of stiffness matrix is 3 by 3. So that is K stiffness matrix. You can write it as a 3 by 3 matrix like this. That is K11, K12, K13, K21, K22, K23, K31, K32, K33. This is a 3 by 3 matrix. This is stiffness matrix which we have to determine. First we have to ascertain the size which is equal to kinematic indeterminacy. Now these elements of the stiffness matrix, by definition, already I told you, we have to go on applying unit displacement along each of these coordinates 1, 2 and 3, one at a time, and then find the corresponding forces. So first let us apply a displacement. Unit displacement corresponds to 1, that is d1 equals 1, d2 and d3. You should restrain. You should not allow a displacement along the other two coordinates. So d1 should be 1, that is along this direction. So you have to give a unit displacement. Here also it is 1, that is kinematic indeterminacy directions. So this is also 1. You have to give unit displacement. This is how the frame displaces. If you give displacement, unit displacement along coordinate direction 2, coordinate direction 1. The other displacement shall make it 0. That is, you show that as fixity. So only the affected members are the two vertical members A, B and C, D. So you just mark all the forces. So this member AB has displaced like that. So because this has displaced like this, there must be a force here. And that force, as per our notation, it is 12 EI by L cube. It is 12 into EI. EI is 2 EI divided by L cube. For the member AB, L cube is 6 cube, that is 216. That is VI by 9. So, when you have a force like this, here there must be equivalent opposite force VI by 9. So, to keep this in equilibrium, this is a clockwise movement. Here there must be anti-clockwise movement like that. This is clockwise, this is anti-clockwise. Now this is perfectly equilibrium, and these forces are like this, and the value of these forces are 6 EI, that is 6 into 2 EI divided by L square, that is 6 by 36, that is EI by 3. This is also EI by 3. And this force is also EI by 9. Now this is perfectly in equilibrium. So this particular thing, you have to mark the forces. That's the only change. And AB has moved like this, and BC, it has not undergone any displacement. So BC, it was like that itself. This is BC. It has not altered. Whereas CD, it has displaced like this. Similar to AB, this also has displaced by unity. So here, of course, all the moments are 0. Here, since displacement is unity, there must be a force here equal to 12 EI by L cube, which is 12 into EI is EI, L cube is 3 cube. That is 12 EI by L cube is 27. That is 4 EI by 9. Here it should be equivalent, opposite, that is 4 EI by 9. So this is a clockwise moment. To keep this in equilibrium, there must be anti-clockwise moment here, which is equal to 6 EI by L square. 6 in EI, L square is 9, it is 2 EI by 3. This already you know. This also 2 EI by 3. Now this is perfectly in equilibrium. These are the moments at the ends of all the members of the frame when you give unit displacement along the coordinate 1, keeping other two displacements 0. Now, you see these elements. So, this particular thing, value, this is the force developed on account of unit displacement in the direction of 1. So, this will be your K11. That's the force along 1 when unit displacement is given at 1. So, this is K11. This particular thing corresponds to 2. That is, this is K21. When unit displacement is given around 1, the moment developed it 2. Here, joint moment, it corresponds to moment this as well as this both. You have to take. This is K21, this is K11, here it is 0, and here, as per our notation, this is also 1, so this is also K11, and this is equal to K31. That corresponds to displacement 3. That is at C. Corresponds to 3. So this is K31. So therefore, K11 is nothing but EI by 9. Then K21 is nothing but EI by 3. And K31 is nothing but minus 2EI by 3, because this is anti-clockwise. Here this is also anti-clockwise, so this is also minus EI by 3 minus 2EI by 3, because they are opposite to these particular things. So you have determined all these elements, K11, K21, K31. First step. Next, you have to give unit displacement along 1, keeping other two coordinate displacements 0. D2 equals 1, D1, D3, you keep it 0. As I told you, to find the stiffness matrix, you should go on giving unit displacement along each of the coordinate direction one at a time in this fashion. First, I have given unit displacement along 1. Now I will give unit displacement along direction 2. That is like this. When I give unit displacement in this direction along 2, so this member will come down, this member will go towards left in this fashion. This will come down like this. So this is how the displacement occurs. And I give one unit rotation along coordinate 2 at the joint B. This is how it will reflect. That you have to mark it first. Similar to beam problems. So the members affected are, and of course the joint C has keep it, here this also has keep it, it's here. So this is that particular thing. Members affected are this AB, it has this space like that individually, AB, this has this space like this, by unity, AB, and BC, that also has this place like this, BC, has this place like unity, this also unity, this is how it has been displayed, this is BC, and CD, it is not affected at all, CD, it has not been affected. There is no force here. Here, since unit displacement is here, there must be a force here in the same clockwise direction. Here also, there must be a force in the clockwise direction. To keep this in equilibrium, there must be equal and opposite force here. So this is clockwise, this should be anti-clockwise. This is one important thing we have to remember here. Because sway is also there, so we have to consider these forces also. Here, this is 4EI by L. So 4EI by L means it is 4 into 2EI, 8EI divided by 6. 8EI by divided by 6 means it is 4EI by 3. 8EI by 6. This will be 2EI by L. That is 2 into 2EI, 4EI by 6, that is nothing but 2EI by 3. Here these two forces will be 6EI by L square, that is 6 into 2EI, 12EI divided by 36, that is nothing but EI by 3. This is also EI by 3. These are the forces developed, moment and shears on account of unit rotation at joint B along coordinate 2. So same thing, this member, since it has rotated like this, there must be a force here in the same direction. Here also there must be a force same direction. To keep this, there will be equal and opposite forces like this. And this we don't require because it doesn't correspond to any of the forces. So only this we need. It is 4EI by L, which is 4 into 2EI, 8EI divided by 6. That is 8EI by 6 means it is 4EI by 3. So this will be 2EI by L, that is 2 into 2EI, 4EI by 6. So it is 2EI by 3. And of course these two 6EI by L square. So that is not required. And this is 0, 0. Now we can attach the elements notation. So here this force corresponds to 4A by 3 and that is nothing but the force developed in the direction of 2, when unit displacement is given at 2 itself. So therefore this is called K22. Force developed along 2, unit displacement along 2. And this, it is not coming to picture, this is the force developed in the direction of 1. This is nothing but force developed in the direction of 1 when unit displacement is given in the direction of 2. So it is K12. And this, it is force developed in the direction of 2 when unit displacement is given at 2. So this is also K22. K force developed at 2, unit displacement at 2. So this is force developed at 3 when unit displacement is given at 2. and these two doesn't correspond to anything, don't write it. So now you can write all these elements, K12, K22, K32 from this. So here K12 that you have determined, K12 is nothing but this is opposite to coordinate given here in this direction. So this is minus EI by 3. K12 is minus EI by 3. Then K22. That is next element. K22 is here 4A by 3, here another 4A by 3, both clockwise, so that will get added up. So this will be 4A by 3 plus 4A by 3, it is 8A by 3, that is K22. Then K32, that is last element, K32 is nothing but, this is same direction as 3 clockwise, plus 2EI by 3. So these are the elements K12, K22, K32, which we have developed the stiffness coefficients. Then lastly is, so you have to give unit displacement along 3. You have to give E3 equals 1, keeping V1 and V2 0. So in order to develop all these stiffness matrices, go on giving unit displacement along each of the coordinates one at a time, keeping other displacement 0 and finding out the forces in the displaced members. So this is how we generate stiffness matrix. This is an important step which already have done in the same thing we are taking here. So first now we have to give unit displacement in the direction of 3, that is here, in the direction of 3, I have to give unit displacement. So that is, I have to give clockwise rotation, this will go, this will come towards right. So it has to displace like that, like this. This is how it will display if you give unit rotation in the direction of that 3 coordinate 3. So this is the rotation we have given. So this goes up, this comes down. And all of us have to keep it fixed. D1, D2, that is, you should not allow to move horizontally. So 2 direction also there won't be any displacement. This is how that sketch looks. The effect members are BC and CD. Only these two are affected by giving this displacement. So this AB is not affected at all. So AB is not affected, so there is no force developed. Only BC is affected like this, which has displaced. So this has affected the unit displacement. So that means when unit displacement is given like that, there must be a force here in that same direction. That is nothing but 4EI by L. That is 4 into EI is 2EI, L is 6. That's 8EI by 6. That is 4EI by 3. 8EI by 6 means it is 4EI by 3. Here you will get 2EI by L. That is 2 into 2EI, 4EI, L is 6, 4EI by L, that is 2EI by 3. And resisting moment forces will be opposite, so that is not being considered because it is not corresponding to any of these coordinates. So next, this is BC, which is affected, and this force is nothing but, this is along 2, when unit displacement is given along 3. So therefore this is K to 3. Okay, yes, K to 3. And this is the force developed in the direction of 3, when unit displacement is given in 3. So this is K33. That also can indicate it. That's the notation we are following. Kij, that is I, O and J curve, that is where displacement force is developed and where displacement occurs. That is as per the coordinates. So next, this number is also affected. It is displaced in this fashion. This is CD. This is that unit displacement has given. So since unit displacement is given like that, there must be a force in that direction, which is nothing but 4 EI by L, that is 4 EI, L is 3. Here in this direction, same direction, of this value, that is 2 EI by 3. To keep this in equilibrium, this gives a clockwise movement. Here it should be anti-clockwise. Like this, anti-clockwise means like this, here it is like that. So this is anti-clockwise. So that is clockwise movement. This force will give anti-clockwise movement, and this is also required because that is corresponds to direction 1 here. So this force is 6 EI by L square. It is 6 EI divided by L square is 9. 6 EI by 9 means it is 2 EI by 3. Here also it is 2 EI by 3. And now we can mark all these forces. So this force is around 3 when unit displacement is given around 3. So that is K33. And of course this result corresponds to that. This is the force in the direction of 1 when unit displacement is given at 3. So K1, 3. That's all. So I have developed K1, 3, K2, 3, K3, 3. So you can write that K1, 3 is nothing but 2 EI by L is in the direction opposite to 1. So it is minus 2 EI by 3, K1, 3. And K23 is 2 EI by 3. Of course, it is in the same direction as the coordinate clockwise. And K33 is here 4 EI by 3, 4 EI by 3, both clockwise. So it will get added up. So it will be 8 EI by 3. So you have found out K13, K23, K3. So all these you have found out. Therefore, you can write K matrix, that is stiffness matrix, as I will take EI by 3 outside. K11, EI by 9. EI by 3 I have taken outside, or EI by 9 I have taken outside. So here it has to be 3. Because K11 is divided by 9, so this is 1 here. 1. K11 is divided by 9. Then K21 is minus EI by 3. EI by 9 I have taken outside, so this has to be minus 3. So minus 3 into EI by 9 is minus EI by 3. So we have to do the same thing. And K31, it is minus 2 EI by 3. EI by 9 I have taken outside, so this is minus 6. So minus 6 into EI by 9 is minus 2 EI by 3. So it is same. K31. Next. Right? K21, K32. 2 EI by 3. So A by 9 is taken outside, 6, 4, 6. Then K12 minus EI by 3, EI by 9 I have taken outside, so this is minus 3. K22, 8 by 3 I have taken EI by 9 outside, so this will be 24. Because 24 into EI by 9 is 8 EI by 3. 24 into EI by 9 is 8 by 3. So the K32 is 2 by 3. I have taken 1 by 9 outside, so this is 6. Then K13 minus 2 A by 3, A by 9 I have taken outside, so it is minus 6. K23 2 by A by 3, A by 9 I have taken outside, so this is 6. K33 8 by 3, that is nothing but 24. So this is our stiffness matrix. This is an important step. How to generate stiffness matrix. Because it is a sway frame, whether it is sway or non-sway, it is material here. If it is sway, only you have to give unit displacement in that direction. If it is sway, you have to give unit translation. If it is non-sway, only unit rotation. Like this. That's all the change. Otherwise, the step procedure is similar. Then you have to find out A inverse. This is a 3 by 3 matrix. You have to find the inversion of this matrix. I will give you the inversion, or you can use your programmer calculator and get the inverse. I have already got this inverse. I will give that inverse. You are going to get as 1 over 90 di into this is 25 3, then 10.5, 10.5, we have 3, 10.5, then we have 7, minus 1, and this value is 9.25. This is the inversion of this matrix. That you have to do, matrix inversion. You have to do the inversion and get that matrix. I am giving you straight away. One thing you can observe here, always all the stiffness matrix what you develop is a square and symmetric matrix. This is a square matrix, that means number of rows is equal to number of columns. And it is a symmetric matrix, symmetric about leading diagonal. All the elements about the leading diagonal, it is similar to the elements above as well as below. So it is a symmetric diagonal matrix, rectangular matrix, and inversion matrix. Inversion of this is also same property. It is also symmetric matrix. You can see 3, 10.5, 10.5, minus 1, minus 1. About the leading diagonal, it is always symmetric. This is an important property of stiffness matrix. That is, stiffness matrix is always a square symmetric matrix, both stiffness as well as inversion. Then the last step, this is second step is the major calculation for the matrix stiffness method of analysis. How to generate stiffness matrix. The moment you generate stiffness matrix, so you can find out PMU matrix also. If you generate that, then last step is only finding the unknown displacement D and unknown member and forces using the standard formula. That's what you mentioned, matrix addition and multiplication. You will get the result. So here PMU matrix, as already have told, it is the matrix, whatever it has been generated when you give unit displacement corresponding to these coordinates, number and displacement. When you give unit displacement along 1, the forces developed along 1, 2, 3, 4, 5, 6, as the name itself indicates. When unit displacement is given along one coordinate at a time, the PM forces develop in all the members that you have to take it. Then along that first column, that is when unit displacement is given along 1, the forces develop along 1, 2, 3, 4, 5. Along 1, force developed is EI by 3. So that EI, I will take it outside. So here it is anti-clockwise, here it is clockwise, so it is minus 1 by 3. Right? Then here along 2, it is anti-clockwise, here it is clockwise, so that is also minus EI by 3, that is minus 1 by 3. And for 3, this, that is BC member, it has not undergone any force, so 0, 0, there are no forces. And along 5 and 6, when unit displacement is given, along 5, it is 2EI by 3, which is anti-clockwise, so this is minus 2 by 3, and along 6, this is again anti-clockwise minus 2 by 3. These are the elements of PMU when unit displacement is given along coordinate 1. Similarly, when unit displacement is given along 2, the forces developed corresponding to these PMs, you can work out unit displacement given along 2, the PMs, corresponding PMs, corresponds to this PM1, that is 2 by 3 clockwise only, so this is 2 by 3 clockwise. Then here it is again clockwise, that is 4 by 3, 4 by 3 clockwise. Then along 3, that is along 3, it is 4 by 3. Along 4, that is along 4, it is 2 by 3. 3 by 3. Along 5 and 6. Along 5 it is 0, 6 is also 0 because that forces is not there because we are not undergoing any displacement. So these two are 0. And lastly, in the PMU method, when unit displacement is given along 3, the corresponding PMs, PM1 0, PM2 0, PM3 2 by 3, clockwise only, positive 2 by 3, okay, it is 2 by 3, and this PM4, it is 4 by 3, 4 by 3, PM5, it is 4 by 3, PM6, it is 2 by 3. So these are PMU. So we have calculated K inverse P. But now step, we have to find unknown displacement, unknown member, then that's all. So for that, we have to use this formula. We have D equals K inverse PD. PD you have generated here. K inverse you have generated. So a K inverse multiply this PD matrix, you will get this unknown. That's all the procedure. So D is nothing but D1, D2, that's the displacement along coordinate 1, 2, and 3. D1, D2, D3, because D is a 3 by 2 matrix which we have generated in first step. K inverse, it is 1 over 17 EI into, that is 25, 3, 10.5, 3, 10.5, then this is 7, minus 1, minus 1, and 9.25. So this is K inverse into PD is this 20, 40, minus 8. So you can multiply these two matrices. So it is a 3 by 3 matrix. This is 3 by 1 matrix. Here number of columns is equal to number of rows. We can multiply. Matrix multiplication is possible when number of columns in one is equal to number of rows of the other. So the resulting matrix you will get as the resulting matrix will be a 3 by 1 matrix, which is nothing but is D1, D2, D3. This is the 3 by 1. This also has to be a 3 by 1 matrix. This is 25 into 20 plus 3 into 40 plus 10.5 into minus 80. That is your first element. That value you are going to get as 1 over bi into 10.6. Similarly, 3 into 20 plus 7 into 40 minus 1 into minus 80, it becomes 24.7. And 10.5 into 20 minus 1 into 40, 9.25 into minus 80, if you sum up, you will get minus 33.5. So this is your displacement along the coordinates 1, 2 and 3 unknown displacement shell. And lastly, number and forces for drawing. So last two steps are straight away using matrix multiplication and using the standard formula. Only calculation is the second step. Generation of stiffness matrices giving unit displacement along that unknown displacement one at a time and determining the values. Also generating PM. So the last step to find, so when we say fourth step, to find member and forces. Fourth step to find member and forces. That is PM. That is what you have to determine during analysis. So we have the formula PM is nothing but PMS plus PMU into B. That's all. And remember the force displacement relationship formula. So this PM, what you have to determine, that is nothing but force corresponds to PM1, coordinates 1 to 6. PM1, PM2, PM3, PM4, PM5, PM6. That is nothing but your MAB, MBA, MBC, MCD, MCD, MDC. That's the member and moments, which is a 6 by 1 matrix, which is nothing but PMS. PMS has generated here. You take that 0, 0, minus 40, then 80, 0, 0. This is 6 by 1. Plus PMU, which we have generated here in second step, that is plus BI into this. And here by 3 I will take it outside, so it is easy. Everywhere we have 3 common factor, I will take it outside. I will get minus 1, then minus 1, 0, 0, then minus 2, minus 2. That is the first row. Then second row, 2, because 1 by 3 I have taken outside. 2, 4, 4, 2, 4, 2, 0, 0. Then third row, third column, 0, 0, 2, 4, then 4, 2. This is your PM2 matrix. 1 by 3 I have taken outside. PM into D. D you have taken here in third step. Let you take it. Into D. D is 1 over BI into 10.6 and 24.7 and minus 33.5. You see this here get cancelled. So this is a 6 by 3 matrix. This is a 3 by 1 matrix. These two you have to multiply. Here number of column equals number of row. Multiplication is possible. If you multiply, you will get a 6 by 1 matrix. So this is 6 by 1. This is 6 by 1. You can add it. Same order. You will get the value of PM. That's all the procedure. So this, if you multiply, you will get, multiply and simplify, you will get this PM1, PM2 and all those things as, because here get cancelled, there's no here, you will get 12.9, then 29.4, then minus 29.4, then 51.8, minus 51.8, then minus 29.4. This is your 6 by 1. So this you multiply, you get 6 by 1. This you have to add it. 6 by 1, 6 by 1, you will get this. So this is nothing but PM1 is this, PM2 is this, PM3 is this, 4, PM5, PM6. They are the end moments which you can use for drawing the end moment. This is about the analysis of a rigid rectangular plane film by stiffness method, direct stiffness method. That is called system approach. This is called system approach because we are using only the global coordinates like that, only force along horizontal direction, vertical direction and moment from positive direction. Only global coordinate directions we have taken. All throughout our calculation, all the directions we have assumed is global direction or system coordinate. That's why it is called as system approach, both for force and displacement analysis. Force analysis, PM, displacement analysis, D, we have adopted only the global or system coordinate system. That's why it's called system approach. Next we have element approach, that is finite element procedure that we use for a truss example. Both are same, more or less similar principle is used. Only here we adopt global coordinates, there we adopt element coordinates and then approach transformation matrix, convert it to global coordinate and do the complete analysis. In fact, for programming on a computer, we use that element approach and not the system approach. For hand computation, the system approach is perfectly suitable. So you got these things. Now you can just plot the bending moment diagram. Because PM1 is this, 12.9 like this, clockwise direction, 29.4 clockwise, you say PM1, PM2, then PM3 is minus. Minus means whatever direction I have taken to start with, it should be reversed. This 29.4. So naturally here, this PM2 plus PM3 has to be 0. That is MDA plus MDC is equal to 0. That's the equilibrium condition that is being satisfied here. So here then PM4 is nothing but this MBC or MCB. PM4 is MCB, that is plus 51.8, plus means same global direction, and PM5 minus means it is anti-clockwise. And lastly is PM6, it is also negative. Negative means anti-clockwise, that is 29.6. Here also MCB plus MCD, it is 0. That's equilibrium condition that is perfectly satisfied. These are the final end moment result. You can just plot the bending moment diagram. After plotting this and superposing the moment diagram, you can plot the bending moment diagram. This is about the we did frame analysis. Same procedure, whether it is sway type or non-sway type. It is now sway type I have taken here. Non-sway also same procedure. Only thing is in non-sway, this sway component will not be there. Only this rotation components will be there. That's all the change. It doesn't make any difference as per the procedure is concerned. Okay. So,